This is the last lesson in Chapter 8, Rotational Kinetic Energy and Angular Momentum. If you hear a little bit of coughing or I have to blow my nose, it's not even 8 o'clock yet on a Monday morning, and my allergies haven't settled down yet. In any case, we're going to look at a couple of problems that we've done in previous chapters, but we're going to be adding a component, angular momentum and rotational kinetic energy, that we did not consider in those problems. And they do make a slight difference in the overall answer, as you will see. Now, you all know what kinetic energy is, 1/2 mass times velocity squared. So you can imagine that if we write the symbols that are analogous to kinetic energy for rotational motion, my mass becomes the letter I for rotational inertia, angular inertial, and my V becomes omega, and it is squared. So when I talk about my kinetic energy, and this is going to be rotational kinetic energy, it's I omega squared. And it looks, of course, and I forgot the 1/2 in there, 1/2 I omega squared. You can see the similarity. So any object rotating about the x-axis, the y-axis, the z-axis with an angular speed is changing its direction as it rotates, and so it's going to have rotational kinetic energy. So not only does it take energy to move something translationally from point A to point B linearly, it also takes energy to move something around an axis, whether that axis is going through the center of mass, in which case it would spin smoothly, or whether it's not going through the axis of rotation, in which case, or the center of mass, in which case it would wobble. Now, one of the key identities used throughout this screencast is going to be something we learned in the previous chapter, that when you want to convert back and forth between velocity in a straight line or tangential velocity and the velocity of something that is spinning, the two are related to each other by the radius of the circle, the distance to the axis of rotation. And so when we take kinetic energy right here, and instead of V, we put in an R omega, we get that, R squared omega squared. And then when we separate out the omega squared, right here, this term right here in the red circle is what you know as the rotational inertia, the moment of inertia, as it's sometimes called. And what this value is, you'd have to look up on the chart 8.1 at the beginning of the chapter. On a test, of course, you would be given what the moment of inertia is for the sphere or the disk or the rod or whatever the object is that is spinning or rotating. And you should know this equation. I should not have to give it to you on a test, because it is the analog to kinetic energy, 1/2 mv squared, that expressed in rotary motion. Now, when you have a bowling ball going down a ramp or a car going down an incline, the wheels are turning, the bowling ball is rotating, and you have three types of energy. We've always considered the gravitational potential energy in the past. We've considered the translational kinetic energy, 1/2 mv squared, and now we are adding the rotational kinetic energy, which we did not include in the previous chapters when we were looking at the work energy theorem. And so one way to define the work energy theorem now is to talk about the kinetic energy that I might have at the beginning of my problem, and the potential energy I might have at the beginning of the problem, the rotational kinetic energy I might have at the beginning, and then look at the end of the problem and look at their final values. And the way I usually like to think about this as expressed down here. I start off with maybe some kinetic energy, maybe some potential energy, maybe some rotational kinetic energy. And it goes to, as that energy is used up to the end of the problem, it goes to these things. And notice I've added a term here to represent any energy that's lost due to friction. Now, normally we're talking about the friction between the bowling ball or the tires on the surface that they're going down. We're not talking about air friction. And we're not talking about the friction that an object might have rotating on its axle, for example. So your book uses W with a small nc for non-conservative work that is lost to heat eventually because of friction. And of course, work is force times distance, and the particular force is the force of friction acting along the distance when that friction is going to be manifest. So you might recall we could have had a problem like this before, like a car or a skier going down an incline, and we simply said we had all potential energy to begin with, and at the bottom we have all kinetic energy, and conveniently the mass is canceled, and it was very easy to find the velocity at the bottom of the incline. Well, with a bowling ball, and even with tires rotating, we neglected to worry about any of the rotational kinetic energy that might be involved. And it makes a little bit of a difference. So if we take our work energy theorem right here, and the ball at the top of the incline has no kinetic energy, so it goes to zero, and it's not spinning yet, so there's no rotational energy. All it has is potential energy, and that potential energy, mgh, has to do with the height. Notice that the height is from the center of the ball at the top to the center of the ball at the bottom, but that would be the same distance as this. We're using the capital letter M here for the mass of the ball. Now, where does all that energy go? Where does the potential energy, how does it get used up? It gets used up along the way as the potential energy becomes both kinds of kinetic energy, and then at the very, very bottom, the potential energy goes to zero, and so that's why this is a zero here. And we have the kinetic energy of the ball at the bottom, but we also have the energy of the ball spinning about its axis. And remember, it's a solid sphere. Any object that's spinning around its center of mass, there's a resistance to that spin, and that's where we get the rotational inertia from. So if you go to table 8.1 and you look up what is the rotational inertia for a uniform solid ball, not a hollow ball, but a solid ball, the two rotational inertias would be different, and it's 2/5 mass radius squared. So you can see that 2/5 mass radius squared is right there. So here's my 1/2. Here's my rotational inertia I. And then here is my omega squared right there. And again, remember that identity that R omega equals V. And so my R squared omega squared right here becomes V squared. So now when I add, I plug my numbers in, and one thing I want to do is cancel out the masses, which I've done right here, cancel out the masses. And now I plug all my values in after I solve for V. Most people like to plug their numbers in and then solve for V. The professional way of doing it is you solve for V first, leaving everything else in variables, and then you plug your numbers in. And you get about 5.5 meters per second. Now you can do this problem over if you want and ignore the rotational inertia, and you would get a slightly different answer. Now, you might recognize this problem as well. This problem we had in a previous chapter, work energy theorem. I think it was back in chapter 6 or 5. But this time we're adding in one more twist. We've got this wheel here, this pulley, that previously we just ignored whatever energy might be involved as this pulley resists spinning. It's rotational inertia. But now we're going to do the whole problem over again, but we're going to include that value. Now, your textbook likes to approach it like this, that the energy you lose due to friction, or that is true, the friction of M1 right here going over the tabletop is going to equal the change in the translational kinetic energy, the rotational kinetic energy, and the potential energy. I kind of like to use this method right here, where I begin with what's the total energy that I have to start with, the source of the energy that's going to drive the system. And that's going to be M2, this block, falling a certain height. Let's say it's falling from here to here, a certain height, which of course is going to drag this block a certain distance across the tabletop. And that distance, delta x, is the same as h, because they're connected by a string, and the string is not going to get bunched up and it's not going to get stretched out. So the source of all of my energy is going to be M1, block M1, falling from one position down to some final position. Now, as it falls, how is that energy being used up? Because energy must be conserved. Well, we know that as my block falls from here down to here, when it gets to this position right there, it's going to have a certain amount of kinetic energy because it hasn't hit the ground yet. And we know that the block up here is going to be encountering friction as it moves through a change in position of delta x. So the work that's done to overcome friction is going to be the force of friction times x. And there's also going to be energy to get that wheel to spin, because the wheel is going to resist spinning. It has rotational inertia. That's 1/2 I omega squared. And the block itself is going to have some kinetic energy when it reaches its stopping point, where it gets blocked by the clamp on the pulley or whatever. So we've got all of that energy going into 1, 2, 3, 4 different places. Now, you might remember that coefficient of friction is defined as the force of friction divided by the normal force. And of course, the textbook likes to use F sub k, lowercase f sub k, meaning the kinetic frictional force, and they use lowercase n. I like to have all my forces designated with a capital letter F, and then the subscript denoting what kind of force it is. But be that as it may, we therefore know that your force of friction is going to equal mu times the normal force. And this is for the block. Well, you might also notice up here that since this is on a horizontal surface and not accelerating in the vertical direction, that the normal force, F sub n, is going to equal F sub w. So down here I can say my force of friction actually equals mu times my force of weight. And my force of weight, of course, is mass times gravity. So, and there's an awful lot of writing going on here. Let's change colors. So when we take this big equation right here and start plugging our numbers in, and what I have up here, of course, is not in the same sequence as you see down here. But when we plug our numbers in, I'm going to come up here. We know the masses, so I'm going to check off all the masses. And we also know the coefficient of friction, mu. And that's given to us in the problem. The thing that I wanted to point out is we're going to have to go to the table 8.1 to find out what is the rotational inertia for a hoop, for a wheel where all the mass is located around the edge, for all intents and purposes, in this pulley. And we're going to have to plug in all of those values. And when we plug in all of those values, which we will do after we find V, again, a lot of students like to plug in their values here and then solve for the velocity. Your textbook takes the more professional approach where they solve this equation for the velocity and now they plug in their values. They do not show you in the box here what values they plugged in, but those are over here. And so you get a velocity of 3.83 meters per second. That's a lot of variables that have to have values plugged in for, and a lot of equations. And I'm going to go back there and remind you of a couple of things. So we have this equation right here, up equals down. And we have this equation right here from the definition of the coefficient of friction. And then we have our work energy theorem. And then we also have the value for I that we have to pull off a chart. A lot of details to attend to. All right, let's talk about the other part of the end of the chapter called angular momentum. And the best example of angular momentum being conserved, because momentum is conserved, regardless of whether it's linear or angular, would be an ice skater. And if you can imagine the ice skater, and he or she is going into a spin, and their one leg is out while they're spinning on the tip of their other ice skate, and their hands are outstretched. And as they bring their leg and their arms in closer to their body, their rotational inertia becomes less and less and less, which means that their angular, their rotational speed becomes greater and greater and greater. If you look at this equation before we derive it, the angular momentum, when their arms and their leg are outstretched, they have a big rotational inertia and they're not spinning very fast. But when they bring their arm and their legs, their arms and their leg in, their rotational inertia goes down, because as the mass gets closer and closer in distribution about the center of the axis of rotation, the rotational inertia goes down and then the speed increases. And these two values are equal to each other because angular momentum is conserved. Now let's derive this equation before we go any further. So here's one derivation right here. You might recognize this equation as nothing but the rotational motion analog for F equals ma, Newton's second law. Instead of force, we talk about torque represented by tau. Mass becomes rotational inertia. Linear acceleration becomes angular acceleration. We know that angular acceleration is the change in angular velocity divided by time. And we can separate my change in angular velocity from initial to final, or I should say final to initial. And then we multiply both omegas by I. And so here we get my change in I omega right there in the numerator, and change in time in the denominator. And if we define my I omega right here with the letter L. Now you might wonder, why in the world are we using L to represent angular momentum? And the letter L looks kind of like the angle sign, but just rotated a little bit, that's used in geometry. And when we talk about angles, we think about things moving through a certain angle, and that's how the letter L got chosen. So the letter L stands for angular momentum. So just like linear momentum is P, and that was defined as mass times velocity, angular momentum is defined as L, and it's defined as a rotational inertia times angular velocity. Here's another way down here to define this term. If you remember that momentum equals impulse, we talked about that before. So mv equals force times time, and the rotational inertia analog for that in this line, instead of m we have I, instead of delta v we have delta omega, and so forth. And we solve it for tau, and then tau equals my inertia times angular velocity, and which is defined as my change in L, change in angular momentum. And that's the same equation as you see up here. So the net torque, remember tau is torque, which is the applied force acting along a torque arm, is defined as the equals the change in angular momentum divided by the change in time. So the net torque acting on an object is equal to the time rate of change of the object's angular momentum. How long does it take to change an angular momentum? And of course, it is conserved. And so you can have a diver going into the tuck position, and they begin to spin very, very rapidly. The ice skater pulling his or her arm and legs in close. Another thing that you can do is get a football sometime. This is a terrible picture of a football, and spin it and lay it flat like this on the table, and then spin it as hard as you can, and it'll go into this position when it's spinning fast enough until the spin slows down. And so this would spin slow, this would spin fast, because this has the greater rotational inertia, this has lower rotational inertia, this will spin more slowly, this is going to spin much more rapidly. And this conservation of angular momentum, of course, again applies to just about everything, to macroscopic objects like planets and baseballs and people and bowling balls and so forth, as well as to atoms and molecules. I remember a long time ago, I think back when I was in high school, there was or maybe it was college, I think Chevy came out with a car, and that car had its engine. This is another terrible picture of a car. And it was much sleeker looking than that, but the engine was in the center of the car, and you kind of were sitting on the edge of the car. Well, if this car were to go into a spin, it would spin very, very rapidly, because most of the mass, the engine, is located in the middle of the car. If the engine was in the front of the car, like most cars, or in a few in the rear, then if it were to go into a spin, for example, on a slick or icy highway, it would spin much more slowly. Other examples would be an acrobat as well. And I guess this is a famous ice skater. Here you would have a larger rotational inertia because the arms are outstretched and not spin so fast. And then when the arms are brought in and the legs are close together, your rotational inertia goes down because more and more of your mass is close to the axis of rotation, and your spin goes up. Here's one in astrophysics, and this has to do with the Crab Nebula. There's a picture of the Crab Nebula now in the science hallway here at the school. And first observed by the Chinese a long time ago in the year 1054. It was called a nova. Nova means new. And all of a sudden there was this new star up in the skies that got very, very bright, and then it faded away. And it turned out to be a star that reached the end of its lifetime. And if you think about a star has the gravity holding it together, but it is also undergoing fusion, which wants to blow it apart. And as long as the star is in equilibrium, like our star, between those two forces, the star remains pretty much the same size. But at some time, as you convert your mass into energy, according to E equals mc squared, and the gravitational forces no longer can keep up with the fusion forces, and it's going to explode outward. And a star that was invisible from the Earth suddenly can become very, very bright at that moment for a period of time until it is spread out. Now, we can take pictures of this, not only with various types of telescopes, but also over time, and notice that this thing is expanding as the material of the star has been thrown outward and has the inertia to keep on moving until something might get in its way. Some of these stars, when they rotate, actually have give off a pulse of energy in a certain direction. And as it spins, if it's in the same plane with us on the Earth, we see that beacon of light being shot out from that rotating star, and it's called a pulsar, a pulsating star. And we can use those to gather information about the star and actually about things like its mass and its distance, because we've learned a lot about pulsating stars from how rapidly the pulsations are. So anyway, this is a good example of conservation of momentum again, because as the star expands outward, its rotational inertia is getting greater, and its rotational speed then is going to get smaller. And here's a person sitting on a stool, or let's say a chair that can rotate. And I've demonstrated this in class before. And you have your arms outstretched, so you have your biggest rotational inertia compared to here. And when you bring your arms in, you go from a small speed to a much greater speed as you spin. And in this problem, there are 3 parts to it. We're neglecting friction. You're given some values up here. And so we want to find certain things. We're trying to find what the angular speed is. We are trying to find the initial angular speed, the final angular speed, and letter C, what work is being done going from part A to part B. So finding the angular velocity is not too difficult, because when you go in a circle, you have 2 pi radians in one circle, and you're going to divide it by the time that it takes to go around one complete rotation. Keep in mind that period and frequency are inversely proportional. Frequency is how many times per second, period is how many seconds per time. So the period, represented by capital letter T, is inversely proportional to the frequency. Now in part B, once we know what my initial speed is, we plug it in there. And so here's my initial inertia that's given to me in the problem, and my initial speed. And then when the person brings his arms in tight, his inertia gets smaller, but his speed gets greater, and we solve for that speed. And you can see it is another radian and a quarter greater than it was up here. Finally, finding the work that is done, we can find the change in rotational energy. since we're disregarding friction. We have our rotational kinetic energy at the end, minus the rotational kinetic energy that we started with. We plug the numbers in from the previous part of the problem, and we see that about 7 joules of work was done. Here's another problem, merry-go-round. We have a disk of mass m, and again, that means you're going to be going to table 8.1 to find out about the rotational inertia for a solid disk. And we're given its mass, capital M, and its radius, capital R. And then we have a student with a smaller mass, and we're using, let's see, the student is going to have a smaller r for the distance that they are from the edge or from the axis of rotation, and we have this speed of 2 radians per second. So again, we have 3 parts to the problem. We want to find, first of all, the angular speed. After we find the angular speed, we want to find the change in the system's rotational kinetic energy, and then we want to find how much work was done. So in this problem, and I'm sorry for all the color coding that I did, but there are so many different terms here that are used over again that if you want to know where they got some value, I tried to color code it. So for example, this value here, the rotational inertia for the disk, and we get this from the table for a solid disk, 1/2 mass radius squared. The rotational inertia is 200 kilogram meters squared, and you're going to be using that again. You can see that we're using that again here in another part of the problem. We're using it again in another part of the problem. Now, if we're going to find the rotational inertia due to the student, S here stands for student, and that's for the student, and that's going to be an mr squared, because we're going to consider the student as being like a solid object with all of its mass at sort of as a point compared to the surface area of the rotating disk, and that rotational inertia is 1 mr squared. And so here's the student's mass and the student's distance. They're at the edge of the disk, the merry-go-round, or whatever you want to call that. And so we get the student's rotational inertia, 240 kilogram meters squared. And you're going to need that value again right there. Now, when we add up the two values to get the total rotational inertia of this rotating disk with the student at the very edge of the disk, you add these two values together, and that value you can see is in red. Now, when we find the, here again is the total rotational inertia, there and there, and we're going to multiply that by the angular velocity, which is in yellow right there. You're going to need that value again later on in the problem. And now we can find the total angular momentum when we multiply the total rotational inertia in the purple and pink times the angular velocity. Now to find the final moment of inertia, when the student has moved from being 2 meters from the axis of rotation, and now the student is only 0.5 meters from the axis of rotation, we can find their rotational inertia by taking their mass times their distance, which is only 0.5 meter from the center, and square it, and you get the student's new rotational inertia. And you're going to need that value again right there. So now that the student is only 0.5 meter from the center, once again, we add up the total rotational inertia of the disk and the student in the new position closer to the center times the whatever. We don't know what the velocity is, so we're going to have to solve for that. and we at least get the rotational inertia. The final angular momentum, the final angular momentum is right there, and there's our value omega. So now we're going to apply the conservation of angular momentum right here, and we're going to take the earlier momentum that we calculated, the earlier total momentum, which would have been this total rotational inertia times the angular velocity of 2, and 4.40 times 2 gives me 8.80, and it's times 10 squared. So that's the momentum I started with, and when the person moved closer to the axis of rotation, we have this rotational inertia. The rotational inertia has changed. We're solving for omega, and we see that the speed is now 4 radians per second, whereas before it was only, that's not the one that I wanted, it was only 2 radians per second. So by virtue of the fact that the student has moved from the edge of the disk 1.5 meters closer to the axis of rotation, the person has doubled their angular velocity. We can also look at the kinetic energy in order to find the work that's being done. And the kinetic energy is 1/2 I omega squared. And all of these values that I'm plugging in are earlier in the problem. And now it's just plug and chug time. So we can find our initial kinetic energy and then our final kinetic energy. In both cases, we are taking our 1/2 times our rotational inertia, which has changed when the student changed position, and the speed, which has changed because the student changed position. And you can see that that difference in energy is 920 joules. So the work done by the student then is going to be right down here. And the work that the student did, all by virtue of changing their position, 1/2 I omega squared. This is their rotational inertia far away. I'm closer in. This is closer in. This is far away. So what you have here is the smaller rotational inertia because the student is closer to the axis and a greater speed. And then down here, the student has the greater rotational inertia when the student was at the edge and a slower speed. And the difference gives us a loss of 355 joules. And again, you can always do extra problems if you want to gain some practice.